ownership and intruders can be sent to the Markov decision process to make the velocity actions. Finally, the result of the two chains can be sent to the ownership. For the first manage, we're using the common filter to make error space zoning. First, we get the state of our intruders, position and velocity. Then we find the relationship between the position and the velocity. Once we've done that, we make the prediction formulas. So we're using Gaussian to define the common filter gain. The final step is update the estimation function and also update the covariance matrix. So the second is for the global path-spanning using the harmonic potential field. The reason why we're using harmonic potential field is because harmonic potential field can eliminate a local minimum than the traditional potential field. Here we're using the Laplace equation to solve these local minimums questions. First, we need to solve these Laplace equations. We just transfer the Cartesian coordinate to the spherical coordinate. So once done that, we're using the separate, because the three parameters coupling with each other. So we can separate the variable method to divided three functions. The first one, the R function, second one is phi function, and last one is the set function. So we combine the three functions together once we get the finally functions. So we do another potential field is called the traditional potential field. It's same with the artificial potential field. So once we got two potential fields, we're using Newman boundary condition to combine the two potential fields together. Finally, we get a harmonic potential field function. For the real-time obstacle avoidance, we're using Markov decision process. So there are 5 parameters in representing the state action, state transfer probability, and a reward and discount respectively. First, we need to define our policy. It's a probabilistic questions. After we have the policy, we can make the reward part. Reward part, we can define 2 functions. One is for the state value function. Another one is the action value functions. So our aim is to find the maximum reward from Markov chain. So we need to in-place the maximum reward into the previous function so we can get the optimal function. Then we required reward matrix and policy matrix. Just like these figures, the start point is represented in the yellow box and the end point is represented as the green box. So the -10 represents the boundary, and the yellow, this is a green block, is represent obstacles. We will follow the maximum reward. We will find, follow these arrows, we will find the trajectory. In this research, we just regard as ownership as the center of this field. And this is the intruders. So once we got the intruders, we can choose any blocks in this field. Since, for example, we chose the red block as the goal point. We will follow this maximum reward and find this action. For the object detection, we just need to describe the YOLO, because YOLO used to make use of only convolutional layers. So, and also it have a feature extractor called DuckNet 53. So as the name suggests, it contains 53 convolutional layers. So each followed of batch normalization layers and leakage revenue activation. The reason why we implement YOLO version 3 because as this shown in these figures, YOLO version 3 is very fast than any other algorithm in this figure. Because we need to using the Raspberry Pi's hardware to implement object detection. So Raspberry Pi have limited memory and calculation ability. So we need to implement we need to achieve faster speed in the hardware. Here is the preset value of the YOLO version 3. For the simulation part, the simulation part from scenario 1 to scenario 4 are separated simulation of each algorithm. In scenario 5, there is urban area simulation that puts all the algorithms together. For this part, we just described the hardware in the loop simulation. First, we're using the RealSense camera to detect the image. We send the image to the Raspberry Pi, and the Raspberry Pi is connected to the PICSOC. So sending the moving signal to the PICSOC via the MAVLink. Another loop is publishing the depth from the Raspberry Pi to the ROS. And then using the ROS drive simulation in the Gazebo. Also, we implement PID controller to control the velocity, position, and the heading angle. So we're using empirical method to choose the parameters of the PID controllers. So in this scenario, we're using the uniform motions and the uniform accelerated motion to verify the adaptive comma filter that I built. So the results show the true position and estimate position matched well. So in this figure, there are 3 like intruders in this map. After 10 seconds, the position of the intruders can be estimated using artificial potential, using the adaptive comma filter shown in the yellow circles. Then the area can be separated according to the number of these intruders. This scenario using the harmonic potential field to represent the environment. A harmonic potential field with Newman boundary conditions is developed for the environment with no location of the start and the goal and even the obstacle boundaries. For the object detection part, eventually through 1,000 times iteration and 64,000 for the training batch and the subdivision outputs can be illustrated in the following tables. So in this table, the average of loss reached at 0.11, which is good for 100 database trainings. Also, the value of the class around 0.99, almost 1, so which means this is training models could recognize the test image and classify the character almost 100%. So in this figure, we can see our OnShape can detect this is truck, and also we have can detect the train in this figure. We also train our own OVOC database, so we can recognize the intruders in this figure. So in this figure, there is intruders fly straight to our OnShape. So when it's close to our OnShape, it will choose up direction to avoid the intruders. Also, there are some comparison results between the MDP and the APF. So the execution time and decision time, and also the collision state are the criterion. The number of the intruders are defined as 1. The execution time of the MDP and like this blue bar is represent the decision time, and the green bar represents the execution time. We can see from the 6 figures, the execution time is almost the same between these 2 methods, but the difference is the decision time. The MDP is almost faster than APF, about 5 to 6 times. And also both algorithms, there is no collision happened. Now the number of intruders as defined and 2. But APF is more slower than the previous results. And also there is a collision happened in the like APF method. So now we're increasing the number of intruders to 3. So there are two collisions happened in this method. From these figures, we can see the total time that MDP spent is 5 to 6 times than the APF. So also the gap is widening with number of the intruders. But the number of intruders have almost no effect on our MDP method. So here is a simulation for the real-time obstacle avoidance. This is our OnShip. So for this, finally, scenario 5, we just implement all the algorithm together. So the red plane are recognized as non-intruders. So the yellow plane represents our OnShip. So by using adaptive Kalman filter, the sparse zones and dense zones can be shown in this figure. So red represents dense zones and the blue is the sparse zones. So once the airspace is defined, harmonic potential field could generate global paths. And here in this figure, we can get the 3D path, the start point to the goal point. Now we need to prepare the unknowns intruders for the real-time obstacle avoidance. The purple plane is inserted in the center of the crossroad in the path of our joints. So when our joints reach the crossroad, we will using the camera to detect the obstacle, using the intruders, and then make a real-time obstacle avoidance. So here is the whole process of the algorithm. So we're using this video to show. First, our OnShip is take off and armed, reach the start point. Then our joints will follow the trajectory generated by the global path planning.
No music, no sound, eh?
Yes. Okay, first.
Yeah, you should put some music.
Yeah, of course. So when our drone OnShip just reached the crossroad, we find using the camera to detect the unknown intruders. So once we detect, we make an obstacle avoidance to the goal point. So for the conclusion,
where is the obstacle? Is that a car?
It's another UAV, another drones.
Oh.
It's unknown UAVs because we can train another like a car or other image. We can choose another one.
Mm-hmm.
Yeah, for the conclusion part, we need to a new orchestra developed that simulate that can handle changes in the environment and plan UAVs flight paths based on the traffic density. Second conclusion is the algorithm is capable of safety navigation UAS platform in a dynamic environment where other UAVs are also sharing the airspace. It's using the Kalman filter to do that. So traffic density is various students of the airspace are estimated. The 3D trajectory based on the harmonic potential field is implemented to generate the goal tempting